Good morning. In this video lecture, we are going to discuss about how to find the efficiency of an algorithm. So we can find the efficiency of an algorithm in two ways. One is the theoretical analysis, another one is the empirical analysis. The efficient one is the theoretical analysis. So how to find the theoretical analysis of time efficiency is you have to identify what is the basic operation performed by that algorithm. Then you count how many times that basic operation is repeated as a function of the input size. So what is the basic operation in the sense? The operation which contributes most towards the running time of the algorithm is called as an basic operation. For example, the simple basic operation what we can say is addition, subtraction, multiplication, division, comparison, and moving and traversing the vertices and so on in case of graph problems. So we can formally define this efficiency of a function or the running time of an algorithm. T of n is equal to COP into C of n, where COP is nothing but the execution time for the basic operation, where C of n is the number of times the basic operation is executed. So these are all the example for the problem and what is the input size and what is the basic operation. So for example, if you consider as a searching in particular key in a list of items, the input size parameter is the number of items in the list. The basic operation is comparison. Okay, multiplication of two matrices, the input size is the order of the matrices or the size of the elements or the total number of elements. The multiplication is going to be the basic operation likewise. So next we'll while calculating the running time also we can able to differentiate what is the best average and worst case efficiency. That is how does the algorithm perform on different data sets of that size. Okay, what is an worst case efficiency is which is going to take the maximum of running time of all the inputs of size n, whereas the best case efficiency is nothing but it will take minimum amount of running time for all the inputs of size n. Average case efficiency is nothing but it will take average of running time over inputs of size 9. It doesn't matter like that. You have to take the average of worst and best case. You have to check the efficiency of an algorithm on the random inputs, or you have to distribute all possible inputs of the size n. So the most important factor we have to consider while analyzing the efficiency of an algorithm is nothing but the order of the growth or the growth rate. Okay, that is how does the growth rate increases when you are increasing the size of the input. For example, if the algorithm is taking this uh, efficiency as n square. Okay, so for example, if you double the input size, so for example, instead of n, if you substitute to 2n, so if you take the ratio between these two, that is if you are increasing these things, so 4n square divided by n square. So this term will get cancelled, it is equal to 4. If basically if this algorithm is taking the order of the growth is n square, if you are doubling the input size, instead of n you replace 2n the whole square. If you take the ratio between these two, 4n square divided by n square, you have only this 4. So that how much longer this running time is going to increase in some terms of multiples of constant value. So the typical order of the growth may be this. If you increase the value of the n, so this is going to be the typical order of the growth. Log n into log n square, n cube, 2 power n and n factorial. Okay, so we'll call this as an asymptotic order of the growth. So you have to, which function describes that order of the growth. So you ignore that constant values on some other function terms. Okay, so you have to consider only that function which describes the order of the growth. So what is an order of the growth or asymptotic order of the growth? In the sense, it's a notation which is used to describe what is the efficiency of an algorithm, and also which is used to compare and rank the efficiency of an algorithm. For a problem input size n, it is not actually it's going to count how many times the basic operation is executed, is how the basic operation grows as the value of n increases. Okay, so as I told already, you ignore or neglect the constant factors, and constant doesn't affect the order of the growth rate. For example, if you consider 5n square and 100n square plus 1000, you neglect the constant over here. Both the functions will have the order of the growth as n square. So these are all the some basic efficiency classes or the order of the growth. It can be a constant or logarithmic, either log n or n into log n. If it is n is linear or quadratic, n square, n cube, or in generally n to the power k, exponentiation, and n factorial. So mostly if you are analyzing efficiency of an algorithm, all the problems will fall into this either one of this efficiency classes. So as I said, the order of the growth or the asymptotic order of the growth will have three notations. One is the big O notation, then another one is omega notation, the third one is the theta notation. So all these three notations which is going to describe what is the upper bound, lower bound, and tight bound of an algorithm. The big O notation which is going to specify the upper bound of an algorithm. If you are saying that a function f of n is said to be in big O of g of n, okay, so which has the order of the growth should be less than the order of the growth of g of n. That is, it grow no faster than g of n, which means that the order of the growth of f of n should be less than or equal to g of n. Then the next omega of g of n, which is going to define what is the lower bound of an algorithm. So we can say that a function f of n is said to be in omega of g of n. Okay, so which has to grow at least as fast as g of n. So that is f of n should be greater than or equal to g of n. So which is going to define what is the lower bound of an algorithm. Then the theta of g of n, which is going to define the tight bound of an algorithm. Okay, so f of n is said to be in theta of g of n. We are saying that which is going to grow at the same rate as g of n. So order of the growth should be equal, whereas in big O of g of n, the order of the growth of f of n should be less than the g of n, whereas in omega it should be greater than. So the next we'll discuss about how to find the time efficiency. So we have said T of n is equal to COP into C of n. So we should know how to count the number of times the basic operation is performed. So first we'll discuss how to find the efficiency of non-recursive algorithm. So because in general either you can write it as a recursive algorithm or non-recursive algorithm. So first we'll discuss how to find the efficiency of non-recursive algorithm. The general plan is, first you have to decide on the parameter n indicating the input size, because more than one input parameter the algorithm is going to take. Among those input parameter you have to decide which is indicating the input size. The next you have to identify what is the basic operation performed by that algorithm. Then you have to set up a summation for the number of times the basic operation is executed. Then you simplify the summation using some standard formulas and the rules. So these are all the some of the basic rules. If you have some constant summation over here, the formula is upper limit minus lower limit plus 1. Suppose if you have the summation term I, the value of I will range from 1 to n, means this is going to be the sum of the natural numbers. The formula is n into n plus 1, 2. So the order of the growth is n square. If it is I square, okay, the order of the growth is n cube. So if it is a power I, okay, the order of the growth is exponentiation, that is 2 power n. Then if you have two summation terms, you can separate into two terms. Sum of summation ei plus or minus summation bi. Suppose if the summation term is associated with a constant, you can take the constant outside of the summation, then you can able to simplify this summation. So the first example we are going to discuss is the sequential search. Okay, so you all know that what is the sequential search in the sense. Given a set of n items along with the search key value, you have to check whether this k is present in this list. Okay, so this is an algorithm given in the pseudo code. So the input is an array of 0 to n minus 1 and a search key k. What is the output is, if the search key is present, which is going to return the index of the first element of A that matches k, otherwise which is going to return minus 1, which means that if the search key is not present in the list. Okay, so what is the logic or the idea behind in the sequential searches? So first you move on to the first location of that array, you check whether that search key is present. So if it is at the moment itself you come out of the algorithm, you can return the position of that element. Otherwise, you continue the search in the next location until either the key is found or the key may not found. So when you will occur that key may not found is once if you have searched all the elements in the entire array or in the list. Okay. So we will discuss how to find this worst case, best case and average case efficiency of this algorithm. So we have written in this while loop, so while I less than n and fi k not equal to k. So which means that search key is not present in that particular location. Simply you make the search it in the next location. So I equal to I plus 1. So once if you have the search is present, I mean the search is successful or the search is unsuccessful. So if you are checking if I less than n, if the search is successful, you are going to return the value of I, otherwise you are going to return -1. So we will discuss this worst case efficiency first. Okay. So what is the general plan shows that first you have to identify the input size. So you have the two values. So one is this array element and another one is the search key. Among these you will have this number of items is going to be the input size. So we will find C worst of n. Okay. So when the worst case is going to occur in the sense the worst case efficiency is nothing but which is going to take the maximum running time. Okay. That is the basic operation is comparison. Okay. So you have to say that when the search is unsuccessful or the search key is present at the last position, so which is going to take n number of comparison. So the C worst of n is equal to n. Okay. C worst of n is equal to n. So that is which means that the search key may not present in this. Otherwise, the search key is present in the last position. If so, you are going to do n number of comparisons. Okay. So next we will discuss C best of n. What is the best case efficiency of the input size n is equal to 1. So which means that the search key is going to present in the first position of that array, so that you are going to make only one comparison, so that the best case efficiency is 1. Okay. So the next we will find out what is the average case efficiency. So the average case efficiency, I have said that it doesn't matter that you are going to take this n and plus 1 by 2. That is not the case, but this will true for this case, but that is not the case. So we'll assuming that the probability for this successful search is p and the probability for the unsuccessful search is 1 minus p. This is what the assumption we are going to make it for what average case efficiency. Successful search is P, unsuccessful search is 1 minus P. And the number of comparisons we are going to take in the sense, what is average case efficiency says that you have to check this for random input size. So the element may present in the first position or second or third and so on at the last position, or the element may not present at all. So the probability for the successful search is P divided by N, which is same for all positions. Okay. So let me define what is that average case efficiency. If you are doing in this first position, how many comparisons you are doing? 1 comparisons. So 1 into what is the probability for the successful search is 1 divided by, sorry, P divided by N, plus if the search element is present in this second position, we are doing 2 comparisons. So 2 into P divided by N. Suppose if the element is present in the third position, you are doing 3 comparisons and so on. Suppose if the element is present in the last position, if you are doing n number of comparisons, n into P divided by N. So you have to simplify this. So what we'll get is you take this P divided by N outside. So you will get 1 plus 2 plus and so on The last term is plus n. So you know that this is that simplified summation of n numbers. So you will say p divided by n into n into n plus 1 by 2. So we are simplifying this. 1 plus 2 plus n is equal to summation of natural numbers. So the n will get cancelled. Okay. So if the average case, either the search is successful or unsuccessful. If it is successful, the p equal to 1. Okay. So if you substitute p is equal to 1, so you will get this n plus 1 by 2. So this is what the average case efficiency. If you substitute p is equal to 1 in this equation, so p is 1, n plus 1 divided by 2. If the search is unsuccessful, what is the probability? That is 0. So if you substitute 0, okay, p is equal to uh, 0, p into 0 of 1 plus n plus 1 by 2. So it will either it will take it is again n. Okay. So the worst case efficiency is n. The best case efficiency is 1. The average case efficiency is equal to n plus 1 by 2. So the next example what we are going to discuss is the maximum element in an array. So the problem is, given a set of n elements, you have to check what is the maximum element in an array. So the input to this problem is an array of n numbers. Okay. It can be either positive or real numbers. So you have to display what is the largest element in an array. So what is the core idea behind in this algorithm is, we're assuming that the maximum value which is going to be the first element in this array. Every time you are comparing that maximum value with the remaining elements in an array, if the value present in that position is greater than the previous maximum value, then you are assigning that element is going to be the max value. Otherwise, you are retaining that previous value is the max value. So likewise, you have to check that maximum value with the all the elements of an array. So max val equal to f of 0 for I is equal to 1 to n minus 1. If a of I is greater than maximum value, then you are retaining max val is equal to a of I. Otherwise, previous value is going to be the max value. So you have to compare the maximum value with every element of an array until all the elements are compared. So finally, you are going to return the maximum value. So next we will discuss how to find this efficiency. Okay. So what is that input parameter? Size is n. The basic operation is comparison. Okay, the next step is, as per the general plan, you have to set up a summation which represents how many times the basic operation is performed. Okay, so you have to represent this summation. The loop control variable we have used is I. So I is equal to 0. The upper limit is n minus 1 is equal to, you have to set up a summation how many times the basic operation is performed. So whenever it is entered into the loop, we are performing the comparison is only one times. We are comparing whether a of I is greater than the maximum value. We are doing only one comparison. So you know that how to simplify this. So because based on this constant, the formula is upper limit minus lower limit plus 1. So our upper limit is n minus 1. The lower limit is 0 plus 1. So the 1 will get cancelled. So you will have this efficiency as n. So we can put the efficiency T of n is equal to big O of n. So that is nothing but the upper bound of an algorithm. So as per the general plan for the how to find the efficiency of non-recursive algorithm, identify the input size, identify the basic operation, set up a summation, how many times the basic operation is performed. You simplify the summation, then you find what is that efficiency of an algorithm. The second problem is element uniqueness problem. So what is this problem in the sense, given an array of n numbers, you have to check whether the all the elements in the array are distinct. That is, it doesn't contain any duplicates. You have to ensure that. So the input is an array of element. What is the output is, which is going to return true if all the elements in the A are distinct. That is, it doesn't contain any duplicate. And which is going to return false if array is containing duplicates. So what is the core idea behind in this algorithm in the sense, you have to take the first element of an array, then you have to check whether that element is present in the remaining position of the array from first, second, third and so on until the last element. Then you have to take the second element of an array, then you have to check whether that second element is repeated from third position or fourth position and so on, last position. Then you take the third element, then you compare with the fourth, fifth and so on, last elements. So here it will require two loops. So the outer for loops determines every time you take that element, you compare with the remaining elements of an array. So it will range from 0 to n minus 2. So the inner for loop is, you have to compare with the next elements onwards until all the elements. So that's why the inner for loop will start with I plus 1 to n minus 1. If you are checking a of I is equal to a of 0, at the moment itself you can come out of the loop. That is, the algorithm is going to be terminated. You are returning false. That is, which means that the array is containing the duplicate elements. If not, you are going to check with the next element and so on. If you are checked with all the elements of an array, finally you are going to return true, which means that the array doesn't contain any duplicate elements. All the elements are distinct. So now we'll analyze what is the efficiency of an algorithm. As per the general plan, the input size is n. The basic operation is again comparison, but here you have the two for loop, so you have to set up a two summation. So first we'll set up with the outer for loop. The outer for loop j will range from I plus 1 to n minus 1. The outer for loop I is equal to 0 to n minus 2. Again, how many times the basic operation is performed? Only one times. Check a of I is equal to not a of j. So first we'll simplify this summation. So in the outer for loop repeats as such, I is equal to 0 to n minus 2. If you solve this constant term, the formula is upper limit minus lower limit plus 1. So n minus 1 minus I minus 1 plus 1. So these two will get cancelled. So you will get it as n minus 1 minus I. Okay. So the summation variable also will range to I. So we know that if the summation will contain two terms, we can split it into two separate summation. So that I can split into like this. So summation I is equal to 0 to n minus 2. The first term is I can separate into n minus 1. The next summation, again I is equal to 0 to n minus 2 I. So the two summation terms, sorry, single summation terms, I can split into two, n minus 1, another one is I. So first we will simplify this. Okay, so to simplify that, you will take this n minus 1 outside. N minus 1 outside. So if you take this n minus 1 outside, you will have the constant over here. Okay, so again this what is the simplification rule for this summation term? Lower limit, sorry, upper limit minus lower limit plus 1. So what is that our n minus 2 minus 0 minus 1. Okay, sorry, plus 1. Upper limit minus lower limit plus 1. So n minus 2 plus 1, you will get it as n minus 1 if you simplify this summation. Okay, again this, okay, minus summation of I is equal to 0 to n minus 2 I. Okay, so you have to simplify this. So the formula, as per the basic rules, if you have the summation terms I, okay, so that is, it is a sum of natural numbers, n into n plus 1 by 2. But our last limit is n minus 2. So based on that, if you replace n is equal to n minus 2, so you will get it as n minus 2 into n minus 1. So if you simplify this, you will get it as n minus 1 the whole square minus, so you will get it as n minus 2, instead of, that is, if you simplify this summation, the that is sum of natural numbers n into n plus 1 by 2, but our the last limit it is n minus 2, so instead of n you replace n minus 1. Okay, so you will get it as n minus 2 into n minus 1 divided by 2. So if you simplify this summation, so you will get the answer is n into n minus 1 by 2. So as asymptotic order, we have to consider only the order of the growth. So you can approximately take it as n square. So the efficiency is big O or theta of n square. So the next example is matrix multiplication. Okay. So it is very simple. You are already familiar with that matrix multiplication. Given an input of two matrices of the order of size n, we have to multiply the matrices. So the output, the matrix C is equal to A plus B, A into B is going to be written. So this is the logic for row 0 to n minus 1. Again J 0 to n minus 1. You find out what is that multiplication of these two matrices. So it's very simple to find the efficiency. So because the basic operation is multiplication, you have to set up a summation how many times the basic operation is performed. So here you have 3 for loops. So you have to set up a 3 summation. So the outer for loop I is equal to 0 to n minus 1. Okay, again the inner for loop j equal to 0 to n minus 1. Again the one most inner for loop k equal to 0 to n minus 1. Okay, so again, how many times you are doing to only one times. Whenever it will enter into the loop, it will perform only one time the multiplication. So since it is a constant term, if you simplify this, what is that formula? Upper limit minus lower limit plus 1. So k equal to 0 over. So n minus 1 plus 1. Okay, so the minus 1 plus 1 will get cancelled. You will get n. Okay, if you take the n constant outside, again if you simplify this, again you will get one more n. Okay, again if you take that n, it will become n square. Again if you simplify this summation, you will get it as the value as n. So that if you simplify this, you will get the answer as n cube. So the order of the growth is big O of n cube, the basic asymptotic efficiency. So far we have discussed 3 examples. So one is that finding the maximum element in an array. The second example is element uniqueness problem. The third one is matrix multiplication. Okay, so if you consider this, the element maximum element in an array, it involves single loop, whereas the element uniqueness problem involves 2 for loop. The matrix multiplication involves 3 for loop. So we can conclude that if the algorithm involves the single loop, okay, the efficiency of class is linear. If the algorithm involves 2 for loops, the efficiency class is quadratic, that is n square. If the algorithm involves 3 loops, we will have this efficiency class as cubic, n cube.